so lit.
Here, we're going to explore square root functions and cube root functions and how to operate with these functions with transformations. So first we're going to look at the square root function, okay? So I'm going to use specific points for the square root function here. Let's say that the square root function is j of x equals the square root of x, okay? I'm going to try to use specific numbers here. For points, I'm going to use the point 0, 0, 1, 1, 4, 2, 5, 6, 7, 8, 9, 3. And the reason why I chose those 3 specific points is because when you square root 0, 1, 4, and 9, you get numbers that come out to whole numbers, okay? Those are key points that I picked. Now, to analyze this particular function, we got to look at intervals of increasing, decreasing, max, min, domain, range, intercepts, and end behavior. Okay, so the intercepts here happens to be the same. The x-intercept and the y-intercept is the same value, so it's 0, 0. The range is how high and how low the graph goes up. So the graph goes from 0 to infinity because it keeps going up forever. Looking at this arrow, the values will keep increasing forever. The domain is also from 0 to infinity because it'll keep going. The x values will keep increasing. Just like the y values will keep increasing for the range forever, the x values will as well. There'll never be a negative x value because you can't square root the negative values, and therefore you can't get a negative value out of the square root. For the maximum, there is no maximum. It'll keep going up forever. It'll never reach an absolute maximum. The minimum is the lowest point, and on our graph here, the lowest point happens to be 0, 0. So for decreasing, that would mean where is the rate of change negative? Well, this particular function doesn't, in this form, does not have any intervals of decreasing, but it does have intervals of increasing, and the interval of increasing happens to be for the entire domain, it increases. Now for end behavior. End behavior is like if we're looking at the graph, what's going to do if we look to the left, what's going to do if we look to the right. So as we're looking to the left, the end behavior means, so as x approaches 0, as we're going to the left, y will also go to 0. It won't go any lower than that. As x approaches infinity, y will also approach infinity. We're looking at really like as we're going on the values of the domain, like if we go to the left on the domain, if we go to the right on the left on the right, left on the domain, right on the domain, we're looking at what the range is going to do. Okay? Looking at what the y values are going to do. So that's the basics of the square root function, looking at specific key features and the graph. Now we're going to try to take this, and we're going to try to graph it. So now that we've looked at the basics of the square root function, we're going to take the square root function and try to transform it. Okay, so here we have a square root function that is transformed from the parent function. Okay, so we're going to try to figure out how to transform this. Well, in this form, it looks a little confusing. Not really sure what's going on here. So I'm going to try to manipulate it just a little bit to maybe make it a little bit clearer for you. So again, this is the parent function. I got h of x here. I'm just going to transform it just a little bit to maybe make it clearer. So we know that order of operations for addition is order does not matter. So if we know that it's a negative 1 on the x, I can think about it like this. negative 1x plus 1 minus 2. Okay? So what we're going to do here is we're going to try to look at the tables and the graph. I'm going to put the graph to the side for a second. And we're going to try to like transform this via just tables. So for my x and y values, okay, we start off with 0, 1, 4, 9, 0, 1, 2, 3. Okay, first thing I want to do is I want to add the 1. We talked about this before. The adding of the 1 is a horizontal translation to the left, so we're really going to subtract 1 from the x values. Do a negative 1, 0, 3, 8, 0, 1, 2, 3. My y values didn't change at all. This is by the add 1. Now we're going to try to deal with this negative. So the negative 1x is going to change all the x values, but it's just going to change the sign of the x values, be the opposite. So this was negative, now it's going to become positive. It's going to be 0, doesn't really have a sign change. These are going to be opposite signs. The y's, again, do not change. Everything we've done underneath the radical does not change the y values. Now we're going to change the y values. So if we multiply by 1.5 on the y's, the x's stay the same because we're done changing with the x values. 1, 0, negative 3, negative 8, 0, 1, 2, 3. Whoops, didn't multiply by 1.5. 1.5 times 0 is 0. 1.5 times 1 is 1.5. 2 times 1.5 is 3. 3 times 1.5 is 450. Okay? Now, we're going to try to do our last part, which is subtract 2. Okay? When we subtract 2 from the y values, again, we're done changing the x values. Now we're only changing the y values. So now it's negative 2, negative 0.5, 1, 2.5. And that should match up with how we're going to transform the graph in a second. Now, our final table here was 1, negative 2, 0, negative 0.5, negative 3, 1, and negative 4, 1, 2, 3, 4, 5, 6, 7, 8, 2.5. So our tables should then match how we're going to transform it from the equation. So this table right here, our final table we created, should match correctly as we do the transformation. All right, so we're going to try to take each part one by one based on the equation and see if we can do the things geometrically. All right, so first, this means we're going to move our original parent function to the left 1. So then the point goes here, 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 and here. Oh, it's making it purple. So this 1 was a horizontal translation to the left. To the left 1. Okay? This negative 1 is now going to be a what? It's going to be a reflection across the y-axis. Okay? That's what we're going to do. We're going to take this pink line, reflect across the y-axis. The point goes here. This point stays the same. This point now goes here. And this other point goes 1, 2, 3, 4, 5, 6, 7, 8, 3. Now goes negative 8, 3. Okay. So we are going to connect here. Okay. So that was orange. Now, we're going to try to take that 1.5. We're going to use yellow here. The 1.5 means that we are doing what kind of stretch? Well, it's outside. It's a vertical stretch by 1.5. Okay? Which means we're taking the y values and multiplying by 1.5. So after we reflected it, we're going to multiply all the y values by 1.5. 0 times 1.5 doesn't change anything. This is 1. 1 times 1.5 makes it go here. And then 2 times 2 times 1.5 is 3. No. 2 times 1.5 is 3. And then here, 3 times 1.5 is 4.5. So our function maps here. And then last, we are going to do the final part, which should match up perfectly, which is the -2, which means we're going to do a vertical translation down 2. So if we look at our graph, well, if I move this down 2, maps to that point, down 2, maps to that point, down 2, all the points map. So we did it geometrically through the graphs and through tables, and our points here from our parent function, or OG, correspond to our points for the new function h of x. So h of x corresponds to j of x through the transformations. Now I want to look at how the key features changed for the parent function to our transformed function. So looking at our h of x here, we're going to try to create new key features based on this function. So looking at our graph here for h of x, which is this green one, it looks like there's no more intervals of increasing because the graph is decreasing all along here, okay? And there is definitely not a maximum either because the graph is not going to reach an absolute maximum. But there is a new absolute minimum, and that minimum is 1, -2. That is the lowest point that our function is going to reach, okay? For our intervals of decreasing, it goes from negative infinity and then decreases all the way until we get to the point of 1. Okay? What's the domain? Well, our domain is now from negative infinity to 1. Our range is from it's from -2 to infinity. The lowest the graph goes is -2, the highest it'll go to is infinity. Our intercepts here are, well, our y-intercept is a little bit hard to see, but if we looked at the graph here on a calculator, based on the graph, there's no way to get an accurate value for the x-intercept, but it's -0.778, 0. The only way you could do that is if you plugged in 0 for y and then solved. But our y-intercept is actually clear because we are able to, that's what transformed to that point is 0, negative 0.5. As far as our end behavior goes, as x goes to negative infinity, y is going up, 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 and up, away to infinity. As x is going toward that value for 1, y is going toward that value for negative 2. So that's how our different key features change for this function after we transformed it from the parent function, aka VOG. All right, we are going to analyze the cube root function. First, we're going to graph it, then we're going to analyze key features of the cube root function. Okay, so I'm picking cube root function, which we're going to call m of x equals the cube root of x. Okay, now for this function here, the key points I'm picking, 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7, 8. Are these points? Because when I create the table for this, and if I were to evaluate them, they would work cube root perfectly, because the cube root of these specific values all give us whole numbers. Okay? That's how I used to graph this from the function m of x. Now let's look at some analyzing, okay? For the intervals of increasing, it is increasing for the entire domain. Even though the slope changes at different intervals, it's still increasing for the entire domain. So the domain actually happens to be from negative infinity to positive infinity. And the range will keep reaching from negative to positive as well, up and down. Okay, the intercept, there's only one, the x-intercept and the y-intercept, 0, 0. The interval decreasing, there is none. There is no max or minimum because it won't reach an absolute max or an absolute minimum. For m behavior, as x goes to positive infinity, which means as x is going to the right, the graph is going up to the positive infinity. So y is going to positive infinity. As x goes to the left to negative infinity, the graph, the function, goes downward to negative infinity. It's very important to interpret these key pieces. We're going to use these, and we're going to create a transformation from this parent function of the cube root function. We're going to create the transformation for this. Okay, we're going to take it step by step. First, we're going to do the table version, and then we're going to look at the geometric version on the graph. Okay? All right, we're going to look at the transformation here from the parent function. F of x equals 2 minus the cube root of 2x plus 1. We're going to do this, and we're going to look at the tables, and then we're going to look at the geometric transformation. Okay, I'm going to rewrite this, though, in an equivalent form, maybe to make it a little bit clearer. This is f of x equals negative cube root of 2x plus 1 plus 2. Okay, so when we actually graph this, it's going to be something to the effect of, well, first we got to start off with the original table, which is negative 8, negative 1, 0, 1, 8, negative 2, negative 1, 0, 1, 2. Okay, and then we are going to subtract 1 from the x values, because of this adding 1 here means we're going to take the x values and subtract 1 to find our corresponding points. So I get negative 9, negative 2, negative 1, 0, 7. And then we are going to multiply by a half for all the x values. So I get, again, we're working with just the x values first, and then we're going to get to the y values. You get negative 4.5. -1, -0.5, 0, 3.5. Now we're done changing anything with the x values. Now we're going to change the y values. So first thing we're going to do is going to do the -1 on the outside, multiply by -1 on all the y values, which just changes the sign on all the y values. Gotta write these all out, and then I get +2, +1, 0, -1, -2. And then we're going to add 2 to all the y values. So I get -4.5, -1, -0.5, 0, 3.5, 4, 3, 2, 1, 0. Our new values. Okay, so we're going to do all of these geometric transformations here, kind of outline them right here, and we're going to do them one step at a time. So the orange is our final transformation. The blue is our parent function, aka the OG. So we're going to start off by doing one part at a time. We're going to do the horizontal translation to the left 1 first. Okay, so every point from the parent function is going to move to the left 1. So that means it goes like this. Okay. Then it's a horizontal compression by 1/2 based on this too. We're dealing with the x values first. Okay, this point doesn't move at all. This point will move to 3.5. This point will move to 0.5. That will move to here. This point will move to 4.5. That's 1/2 of 9. 1, 2, 3, 4. That means our graph kind of looks like this. Okay, then the green, the -1, is a reflection over the x-axis, so we're going to take every point and we're going to reflect it, okay? So this -4.5, comma -2 is going to go up to here. This point's going to reflect to here. That point's not going to move. This point's going to reflect down here. And this point's going to reflect over to here, like this. And then it's going to do a vertical translation by 2. And every point will move up to our orange. Okay? So we did it by, we analyzed the equation with some words, okay, what each part means. We looked at how the parent function translate via tables. And then we also did geometric representation by translating the graphs a bunch of times. Okay, so now we're going to compare the key features from our parent function, which we already did, to our key features for our new function, okay, which is this f of x function, okay? So the interval of increasing no longer exists because now the function is decreasing across the entire domain. Is decreasing across the entire domain. Again, there is no absolute maximum or minimum because the graph will never reach an absolute max or an absolute minimum. The range, though, goes forever. Okay, that didn't change. The intercepts are now the y-intercept, and the x-intercept is now, well, the y-intercept is 0, 1. The x-intercept is 3.5, 0. The end behavior is, as x goes to positive infinity, y goes to negative infinity. As x goes to negative infinity, y goes to positive infinity. So some changes here with the key features. It's very important you can understand and compare how key features change from the parent function.